Next, we're going to look at the technique of logarithmic differentiation. So now that we know how to take the derivative of log functions, we're going to use that to be able to make certain types of differentiation much easier. So here's an example of a pretty messy function. We could use quotient rule to solve this, and I would recommend going on your own and verifying our result using quotient rule on your own. But instead of doing quotient rule, we're going to do something tricky. We're going to take the natural log of both sides of this function and then use some of the natural log rules to be able to simplify our differentiation. So we're just going to take the natural log of both sides by applying it as a function to both sides of this equation. So I get the natural log of y on the left, and then I get x times x squared plus 1 over the square root of x plus 1. Get the natural log of that big messy thing on the right. Why is this helpful? This is helpful because I can use natural log rules to be able to break this up into something that's a little bit easier rather than having to look at each of these pieces individually. So if you don't remember a lot of your natural log rules, I recommend that you go back and revisit one of our prerequisite material quizzes. One of the properties of logs is that I'll keep natural log of y on this side, that the product of logs can be broken up as the sum of each of the logs individually, meaning that this is equivalent to the natural log of x plus the natural log of x squared plus 1 minus the natural log of x plus 1 all raised to the 1/2 power. Now why is this? The product on top becomes each positive terms in the log, and the quotient on bottom becomes a negative subtraction of the logs, and it derives from the properties of exponents. There's one further rule that we can use. Because this whole term has is raised to the 1/2 power, a property of log says that I can move this out as a coefficient on front. So this whole right-hand side becomes natural log of x plus the natural log of x squared plus 1 minus 1/2 the natural log of x plus 1. And again, I recommend that you go back and review some of those properties of logs if you'd like. And all of that is equal to the natural log of y. So at this point, we haven't done any differentiation. All we've done is utilize some rules of logs. But now, let's go ahead and take the derivative of both sides using implicit differentiation, noting that we have the natural log of y on this side. So when I take the derivative with respect to x, I need to keep chain rule in mind, the derivative of this whole chunk with respect to x. What do I get out? Well, we know that the derivative of natural log is 1 over whatever this function is evaluated at, which is y in this case. So the derivative of natural log is 1 over y, but by chain rule, we need to remember that this is multiplied by dy dx, because that's the derivative of y with respect to x. And for this derivative, I can do it piece by piece. Because these are broken up as terms, I don't have to worry about doing it as one big messy quotient rule problem. So for this first term, the derivative of natural log of x is easy. That's just 1 over x. The derivative of natural log of x squared plus 1 is going to be 1 over x squared plus 1. Aha! I almost walked away, but I'm not done yet. I need to employ chain rule because this is a messy function on the inside. The derivative of this inside function is 2x. And then finally, this is going to be minus 1/2. The derivative of natural log of x plus 1 is going to be 1 over x plus 1. And again, we multiply by chain rule. The derivative of x plus 1, though, in this case, is just a line with slope 1. And so the derivative of that is just times 1. And we can simplify this a little bit. What are we trying to find in this case? We're trying to find dy dx. And it means that we don't want to really have this y stuck in here, because we want to have our solution to be written out in terms of x. So instead of having a y here, we're going to have to go back to our original function and plug in what y is actually equal to. And in this case, y is equal to this messy thing. Or 1 over y is going to be equal to the reciprocal of this messy thing. So I'm going to plug in 1 over y using the fact that this is what y is actually equal to. So 1 over y is going to be the reciprocal of y, which is the square root of x plus 1 divided by x times x squared plus 1. This is 1 over y using what y is equal to, times dy dx is equal to 1 over x, and this fraction I'm going to write as a single fraction, 2x divided by x squared plus 1, minus, I can multiply this 2 through and get 1 over 2 times x plus 1. Okay, maybe I didn't distribute the 2. But now we're almost done. What are we trying to find? We were asked to find dy dx. We have a dy dx, but we're going to have to divide both sides by this to be able to get dy dx by itself. So our final solution we get is dy dx is going to be equal to, I'm going to multiply both sides by the reciprocal of this, which in this case is x times x squared plus 1 divided by the square root of x plus 1, all multiplied by 1 over x plus 2x divided by x squared plus 1 minus 1 over 2 times x plus 1. And again, this actually does simplify a little bit, but I'm going to leave it like this as my final answer. So that's a messy example of logarithmic differentiation. If you didn't like this, well, you could always go back and use quotient rule if you decided that this was something that you thought was messy. But there are certain problems that are going to be almost impossible to solve using quotient rule, and logarithmic differentiation makes them possible. We're going to finish off by looking at a couple more examples of derivatives using natural log of x and things of the form b to the x. So this should be easy by now. If this is my function and I want to know what the derivative is, the derivative of natural log is 1 over whatever the function is. I say 1 over stuff, and in this case the stuff is 3x squared. But again, because there's a function on the, this is a composition of functions, there's a function on the inside, I have to multiply by the derivative of the inside, which by power rule is 6x. So this becomes 6x in the numerator and 3x squared in the denominator. And I can simplify, and I end up with 2 over x, right? Because one of the x's cancels, and 6 divided by 3 is 2 in the numerator. For our next example, we're going to look at 8 all raised to the sine of x. If I wanted to, I could rewrite this 8 as e to the natural log of 8, and I could do the same derivation, or I can use the rule that we already found. This is going to be the derivative of e to the stuff is e to the stuff. The derivative of 8 to the stuff is almost 8 to the stuff, meaning that it's almost 8 to the sine of x, but I have to multiply it by the natural log of 8. So that's the derivative of the outside function, this whole big piece. By chain rule, I also have to multiply by the derivative of the inside function, which is sine x, and the derivative of sine is cosine. And there really is no way to simplify this. This is our final solution.